Welcome back to ECE 220. Somewhere I can maybe find where we're at. We're in our last week, essentially. We have one more week of the semester, but this week we have our exam on Thursday. Today will be a review lecture for that, going through the exam from a year ago, fall of 2018. And just as a reminder, we won't be meeting the day after exam number 4, which is this Friday, and we won't be meeting on the last day of class in this lecture hall, which is next Wednesday. But this Wednesday, Group B, if you're in Group B, you need to make sure and submit your report for the last lab, which is lab number 5, and tomorrow you have one of your homework assignments of the 2 that are remaining due, and it is covering Chapter 9 material, which won't be, although there will be one problem dealing with phasors on exam number 4. Let's get started with the review for exam number 4, and what I thought I would do, and again, this is for last fall's class. There are 12 questions. I thought what I would do is I would jump back and forth between part 1 and part 2, so I don't spend the whole time on part 1, which is just a third basically of the points that you have available to you on exam number 4. You should get very comfortable with the formula sheet and understand when you need to apply the A, the B's, and the D's, whether that's overdamped, which are the A's, the underdamped, which are the B's, and the critically damped, which are the D's. And in these formulas, there's a T0, which is the delay amount. That's if you switch at some time other than 0. And I think one of the problems today, if we get there, we'll work through that. The other thing to remember, and it's not on here, so you'll have to write that down maybe when you first start your exam, is the natural frequency, omega naught. That's 1 over the square root of LC, and this relationship between alpha and omega naught if you have underdamped roots. If you have underdamped roots or an underdamped system, you have complex roots, and they are, let's say, at those X locations. This distance is alpha, and this distance is omega sub d, the damped frequency, and that may be asked for on one of the problems. And the hypotenuse of this right triangle has a length that is equal to the natural frequency omega 0. If that gives you a better way to think about finding omega sub d given alpha and omega naught. When you're faced with an RLC circuit, it's best to say, okay, is it parallel or series in this class? Is it a parallel RLC or is it a series RLC? Find your alpha, depending on which of those it falls into. Your omega naught is the same, and then compute the 2 roots, S sub 1 and S sub 2. And if the argument underneath the radical is negative, that means, in fact, that you are living in this underdamped case, and the imaginary component of those complex roots, that's the omega sub d. That's the damped frequency. Let's get started and begin on page 3, part 1, with the first problem, which says, at what time t will the inductor current be approximately 0? And what you want to be aware of is, are they putting some switch in, which in this case they did, And once that switch is thrown, you essentially have that remaining sub-circuit to deal with. But because that switch is thrown at some time other than 0, your final time is actually going to have this offset of 4 milliseconds. And then you add to that what we've been talking about in terms of infinity, which is 5 time constants. And now so there's two sort of parts to this problem. One is remembering the offset to take it into account, and the other one is finding the time constant tau. And the time constant is found, this is a first order RL circuit. We now simply need to focus on what's remaining when that switch is then thrown. And now we have an RL circuit, and hopefully you can see that, I don't know what color to use, that this series combination of the R's is your effective resistance value in that RL circuit. Or your R now is 3 plus 4, or 7. Your L is just the 42 millihenries. And now you could either write that as 0.042 or keep track of the milli. It's whatever you find more intuitive or clear for you. But now the time constant tau, and this isn't on your formula sheet, so you'd either have to rederive this or remember it. But maybe one way to remember it is that the resistors are always in the basement, or they're always downstairs in your time constants. One time constant for RC is 1 over RC. So C's are downstairs and L's are upstairs. So now if you have an LR time constant, it's L over R for the time constant here, or your R is in the basement of that time constant. If you had an RC circuit, then you have a time constant of 1 over RC. R is in the basement. C's the capacitance, and when you remember, well, I'm getting into chapter 9. So let's just focus on chapter 7, which is RL circuits. Now we have tau. Or we now have 6 milliseconds for tau. 5 of those gives us 30. And we add the offset, which is 4, and that gives us 34 milliseconds for our answer to problem 1 in part 1. As I said, are there questions on that circuit or that problem? Hopefully I have this organized. I said I was going to jump back and forth so that we didn't focus all of our attention on part 1. So let's now go to the first problem in part 2, which is problem 7, which is a phasor problem. So just be clear that you are going to have to play with complex manipulation or algebra with complex numbers. And here, the question is being asked to find that voltage. Find the phasor voltage, V under bar. I might have it V over bar bold. It's a phasor. It's some complex number. And your answers are in the form of complex numbers, a magnitude and an angle, or a magnitude and a phase. And here, you need to try to figure out, how am I going to analyze this? What can I do with this problem? You're given this node voltage. You could do mesh analysis, but then that's 3 mesh currents, and that's not even giving you the answer directly. You would have to use that mesh current and multiply it by J8/3 to get your voltage. What if we did node voltage analysis? Well, we're given the blue node. We need to find the red node, and that node is also unknown. And I don't know if this will make it even worse, but let me call this node voltage V sub 1 as a phasor. So we have black, red, and blue node voltages. The blue node voltage is given. We should be able to now find the phasor voltage V underbar from just writing 2 node voltage equations and solving for that second unknown. We have a black and a red that we need to find, those node voltages. We can write their 2 node voltage equations and then solve for, this is now 2 equations in 2 unknowns, and these 2 unknowns are complex quantities. Don't let that scare you. You just have to run through the math with complex numbers. So if we wrote the equation, let's say for the red node, now we have all of these, and maybe I'll just say, let's say the sum of those currents are going out of that node, and they all sum to 0. The vertical current going up, should I write it in red, or is that too frightening on a Monday morning? It lets you know that we're doing the red node. We now have V underbar minus V1 bar over 8. That's the current going up out of that node. Then we have the current going to the left horizontally. That's V underbar minus 22 minus J33. And you could convert that or not to a polar form. It's however you want to get comfortable playing with it. And then we divide by the impedance that voltage drop is across. And finally, we have our current going vertically down, which is V underbar J8/3 is equal to 0. That's our first node voltage equation. Just KCL at the red node. Now we can write KCL at the black node, and we do the same exercise. Whoa, like I said, I have no idea what's going to happen today, but we now have these currents that we can sum. So in this case, we have, let's say the current going down is V1 bar over 8 plus V1 bar minus the 22 minus J33 over minus J4. That's the horizontal going to the right, plus V1 bar minus V underscore bar over 8 is equal to 0. Now, what you have to do is just take a deep breath and plug through the math. And it might be more, or it might be cleaner to just clear the denominators. And you could clear those by multiplying by 8 in both cases, and realizing that J's downstairs, or when you do this division by j or minus j, things change signs, meaning if we now had 1 over minus j, that's equivalent. We can multiply it by 1, which is j over j. We now have j squared downstairs with a minus. That's a minus a minus. So that ends up being j. Or if we just had 1 over j, then to bring that upstairs, now that's a minus j. If you wanted to get that j out of the denominator, you can by the appropriate conversion or multiplication by 1. I think it would be more instructive for you to solve this on your own after the fact without me, because I'm afraid if I start working through the analysis, you're going, yeah, I got it. And then come Thursday, you're going to go, I don't know how to do this complex. So do the complex math. If you have questions, come see me during office hours, but the correct answer is there, is C. It ends up being a purely real voltage. Now don't expect that to happen necessarily with me making the problem. Dr. Marsland obviously spent some time figuring out what things needed to be, and in particular, starting with a voltage source of 22 minus J33. And now that, with all the other impedances, allows you to obtain a real answer. Is it clear the steps? I would again clear the denominator, and then you have 2 equations and 2 unknowns. So now we're back to page 3 and problem 2 in part 1, well, problem 2 on this exam, which is, suppose the following differential equation describes an RLC circuit. You don't have to know where, you don't have to know the circuit, you don't have to even know how that was obtained. Now this is just given to you. And you have to figure out, oh, if I'm solving that circuit, is that circuit overdamped, underdamped, critically damped, undamped, or none of these? And you'll do this until you're tired of doing this in 320A, is playing with S's. But here you could say, okay, here is my structure for the solution. If we now look at the derivative of that with respect to time, that's SA e to the ST. And if we differentiate it twice, all that being said, now we replace those expressions for x, the second derivative of x, the first derivative of x, and x by itself to find our characteristic equation, which is found in the homogeneous case, which is when we don't worry about this driving force or the input. Or we're now looking at 2 x double prime, which is s squared a e to the st, plus 4sa e to the st, plus 2 a e to the st is equal to 0. And we're assuming a non-trivial solution, which means that our x better be something other than 0. We can divide that common factor out, and we now have 2s squared plus 4s plus 2 equaling 0. What you're trying to find is this quadratic expression. Now you can plug it into the quadratic formula. You could factor it out, 2. You could do all sorts of things to do this. If you factor a 2 out of that, you see maybe, and you don't have to do it this way, but you now see s squared plus 2s plus 1, and maybe you can see then that that is, in fact, s plus 1 squared. So you actually have two values of s equal to minus 1. You could, if that doesn't make any sense, just plug the 2s squared plus 4s plus 2 into the quadratic formula, find where your roots are, and then determine what case do I have. When is it overdamped? What values of s do you have if you have an overdamped response? Are they complex? No, they're real and unequal. That's overdamped. Underdamped, complex. That's when we have real and imaginary components to our s's. Critically damped is when we have two real equal, and that's what we have here. We have two roots at minus 1 both. They're both at minus 1 because that quadratic expression factors into s plus 1 quantity squared. So in this case, we have critically damped. What would be undamped? When they're complex, but the only component is they have an imaginary component. There's no real component in the complex. They're on the imaginary axis. It's plus and minus J7 or something, plus and minus J2. They're purely complex. That's undamped. The alpha, so alpha is 0. But you don't know what alpha is because you weren't given a circuit. But here you would be seeing something like s squared plus 1 is equal to 0. That's not the case we have here, but this now says s squared is equal to minus 1. Now we have s is equal to plus and minus j. That would be undamped. And if you were looking closely, that means you don't have that linear term to give you some damping. It was missing. All right, we're jumping around. We're doing our calisthenics today. Let's now look at problem 8. Given some initial conditions, find the time rate of change of the voltage across that capacitor at 0 plus. And the thing you have to be comfortable with in this exam is Eli and ice. And here we have we have an RLC circuit. Ice, the last variable is voltage. Eli, the last voltage is current. And why am I emphasizing those? Those are the ones that cannot change instantaneously. Capacitor voltage cannot change, so if you know it at 0 minus, it's the same at 0 plus. If you know the inductor current at 0 minus, it's the same at 0 plus. The other two variables related to inductor and current, they can change instantaneously. And here, we are wanting to know what's the slope or the time rate of change of the voltage of that capacitor at 0 plus. And we're given this voltage at 0 minus. So this now says, oh, that's the capacitor's voltage. We know it now at 0 plus. The I is the inductor's current. We know that then at 0 plus. And do we now have enough information? Well, ice tells us that I sub c of t is equal to c dv sub c dt. And we're actually trying to find this. at time t equals 0. But if we could find this at t equals 0 plus, we could solve for the derivative at 0 plus, because that's just a proportionality away from the current, where the proportionality constant is c. We're now looking for the capacitor's current at time 0 plus, and we can find that by writing a KCL equation at that single node in this equation, or in this circuit. Let's call this, and now this current, and pay attention to this as well. By the passive sign convention, I'm now defining I sub c consistent with the passive sign convention. In some of your problems, they may be messing with you and putting a current or a voltage opposite to what you would expect it to be. But now, and let me now say that this one is I sub r. KCL now allows us to write I sub c plus I sub L, which in this case is just I, plus I sub r is equal to 0. We know I at 0 plus. We're trying to evaluate this at 0 plus. Do we know I sub r at 0 plus? Can we find it? We know the voltage across that capacitor is not changing between 0 minus and 0 plus, and that capacitor is in parallel with everything else, so that voltage is being shared across all three of those elements at 0 plus. We now can find I sub r at 0 plus. We know I sub L at 0 plus. That was in fact given. Knowing that it can't change instantaneously, we can now solve for I sub c at 0 plus. And once we have I sub c at 0 plus, we can back out the derivative of v sub c at time 0 plus. Meaning, I sub c of 0 plus is equal to, what was this? This was 10 milliamps, I think. That, whoops. Let me just keep it going this way. Plus 10 milli plus I sub r, that was 18, I think, for our v sub c of 0 plus, divided by 9. And that was k is equal to 0. Now we know that I sub c of 0 plus is actually minus 12 milliamps. And we can now use this equation to solve for dv sub c of 0 plus dt is now I sub c of 0 plus over c. Or that's minus 12 milli over whatever c was, which was 1 times 10 to the minus 6. Minus 12,000 volts per second. And I think that's one of the answers. Did you follow the steps or the process so just try to think through what you have, what you know, and using Eli and Ice, a lot of times you can back out what you need if it's a derivative's initial value at some time. Problem 3. Find I of 0 plus. And I is an inductor current. And we have a switch, and it switches at 0. But what do we know about the inductor current? Eli, I, it's the last variable in that Eli expression. I cannot change instantaneously. If we can find I at 0 minus, we've got it at 0 plus. Can we now find I at 0 minus? So now the switch is in place, and it might be beneficial to redraw this circuit. So now, and it's been in that state for a long time before 0. What will then happen? What will this circuit look like? Well, we can just say, okay, we have 16 milli here. We have a resistor there, a resistor there. This one's 3K. This one's 5K. This is 8K. You know what those are, even if you can't read them. That inductor has been in that state for a long time. It now becomes a short. And now can we make any other adjustments to that circuit? We've now drawn the circuit in a steady state condition. This is now for t less than 0. Can we make any other adjustments? Or can we modify this circuit, or is it as good as we can make it? Do you see that that inductor is actually shorting out that 8K resistor? So this is, we don't need to worry about that 8K. All current from here and here is going to flow into what we want, which is I. So if I labeled this I5 and this I2, if I could find those, I could find I through KCL. And if it's too confusing, you have two independent sources, you could apply superposition and then add up the net result. You could say, well, let me just do this one source at a time. This is too confusing. I see some fingers. I lost you after everything shorted out. So, oh, so now why do we have to worry about the 8-volt source and the 2K now that we have that wire? Is that what you're asking? I think. So now what we need to keep track of, though, is the current in that inductor is actually getting current from both sources, the 8-volt source and the 16 milliamp current source. And so we can't neglect that 2 and 8 because, well, if it is shorted, that means that actually simplifies our analysis. We can find I sub 2 because that 2, what's the voltage dropped across that 2K resistor? 8 minus the common, 8 minus 0, divided by 2K. That gives us I sub 2. What's the current I5? Are we okay with what I just said on I2? Or if you wanted to, you could do it with superposition and just say, let me forget what's on the left and just find I due to the 8. And then let me forget what's on the right and just find I due to the 16 and add them together, and I'll end up with the same answer. I'm doing it at the same time by saying I2 is 8 divided by 2k. That's because this point, relative to the 2k, is that point, which is common. All 8 volts is dropped across that 2k. I sub 2 is now 8 divided by 2k, or 4 milliamps. What's I5? Well, this point, again, is that same point right there. And that point is the same as that point there. The 3 and the 5 are in parallel relative to that 16 milliamp source. We can do a current divider to say how much of that 16 is getting through the 5 and how much is getting through the 3. If they were equal, then we would have 8 milli going through both, but they're not equal. So how much current do you expect through the 5K? More than 8 or less than 8 milli? If you do a number and you get an answer, are you looking hoping that answer is above 8 milli or below 8 milli? Is this making I'm just trying to give you a way to think through in the heat of the battle. Oh, I got a number. Good, that's all I need. No, kind of be clear on where your numbers are coming from and what they look like. Current divider here is now 3K over 3K plus 5K times the 16 milli. We have 3/8 of 16, something a little less than a half. So it's under 8, which is good. So now we could say, oh, we divide the 16 by 8, we get 2 times the 3. I sub 5 is 6 milliamps, which says then that I is equal to I sub 2 plus I sub 5, 10 milliamps. That one was kind of tricky in terms of figuring it out. But if it really messes you up, say, wait a minute, I've got 2 sources. Let me just treat each one independently. I can use superposition and add up my results. If this made you feel uncomfortable, this analysis, just say, forget the 16 milliamp source and let me just solve it for the 8 volt source. Oh, I is 4 milliamps for that situation. Then let me forget the 8 volt source, zero it out, and now I just have 6 milli coming through I because all the current is going through that shorted path. Should have numbered my pages. Whoops, that's not the page. We want 9. Find the damped frequency of the following circuit. And is it clear what that damped frequency, that's with a P. You may be saying it otherwise on the exam, but that's D-A-M-P-E-D. Damped frequency is omega sub D. So they're kind of telling you that, wait a minute, I probably need to find the roots of a quadratic, and those roots better be complex, and now I just need the imaginary component to obtain omega sub d. Now, how do we find, or when we're analyzing a problem, when we find the characteristic equation, we're looking at the homogeneous circuit. How does this circuit naturally want to respond? What's its characteristic? In this case, then, to find the characteristic equation, we're looking for the homogeneous circuit, which says, oh, set your sources to 0. If we set the source to 0, we don't need to worry about that 10. We set it to 0. That's a voltage source. We can short it. Now, we look at this circuit and we say, can I make this into a parallel or series RL circuit? Or is it a parallel or series RLC circuit? Do you see now that I have 265s in parallel? And that parallel combination, that parallel combination is in series with 30. So this is now half of that, or 32.5. I now add that to the 30 ohms, and how can I simplify this? How do inductors combine in parallel? Like resistors, so this will actually be cut in half. This is now 20 millihenries. That's 40 times 40 divided by 40 plus 40. How do these combine? Capacitors in series. Those now combine like resistors in parallel. So this is now 6/3 divided by their sum. We now have 18/9, or that's 2 microfarads. Are we clear with what I'm trying to hint at? We now have one resistor, which is 32.5 plus 30. We have one inductor, which is 20 millihenries. And we have one capacitor, which is 2 microfarads. And they're all in parallel. We have a parallel RLC. And now we can use the alpha for that. And you will have this formula sheet. You go over here and you say, oh, alpha is 1 over 2RC. Now, where was I? And if you plug in the numbers, you end up with 4,000. Omega naught. With that L and that C, you end up with 5,000. And now you could do a sanity check. Is this really what you need? If they're asking for a damped frequency. You now want omega naught to be bigger than alpha. Or omega naught squared is bigger than alpha squared. And it is. We now have this right triangle picture that we could draw. We could say, oh, this is 5,000. This is 4,000. And now I'm trying to find this omega sub d. So that omega sub d is the square root of the hypotenuse squared minus the adjacent side squared. And doing that, you end up with 3,000 radians per second, or 3 kiloradians per second. Here's another characteristic root problem. So let's just, this is now problem 4. And this is after t greater than 10. So now we're just focusing on that subcircuit of the overall. We can quickly see that those combine to 10 microfarad, and these combine to 10 ohms. And now we have a parallel RLC. We can find alpha and omega naught, and in this case alpha is bigger than omega naught, so we have overdamped, and in fact we have B. I'm kind of speeding up, but we've kind of just went over one of these. But you just say, okay, what do I have left beyond 10, and can I simplify to obtain an RLC circuit, series or parallel? This is a series RLC circuit. That immediately tells you you can go back to your formula sheet and find the proper alpha. This is R over 2L. And plug that in, and you end up with 3,125. Omega naught is always the same, 1 over the square root of LC. You plug that in and you get 2,500. What kind of a circuit behavior do you have just based on those two numbers? It's overdamped. Alpha is bigger than omega naught. It's now overdamped. And which of these are we playing with? A, B, or D? A's, B's, or D's? And when you first come in, if it's not all that obvious to you, just write down, oh, this is over, under, and critical. And hopefully none of us will be critical at the end of the exam. We're now overdamped. We're looking for A's. And you can now use those bottom two equations. You're given x at time t0, x at 0, t0 is 0. You're given the time rate of change of v at time t0, which is 0. And now you can solve for A1 and A2 using those equations. Because what is x at infinity in this example? What's the voltage going to be at infinity? Do we have a tank circuit? The tank is if that resistor was gone. We have resistance. This is going to that resistor is dissipating all the energy in that circuit. We're going to have 0 volts, so we don't have to worry about V at infinity, and those two formulas simplify a little bit. You know what? Let me quickly, in the 10 seconds we have left, let's talk about this. We are asked to find V at time t equal 10 milliseconds. Here, Fifi, Fief, whatever. F-I-F-E, Fife. That's probably what you want to use. On these first order, this is first order, it's an RC circuit. What's the final value of that voltage V? Do you see that it opens up and all you have to do is figure out how much voltage drop you have, and you know what current's going. It's 1 milliamp through 1 K. That's 1 volt for the final value. You're given the initial value. Now what you need to do is find the time constant. Which is RC. What is RC? Do you see that if we set the source to 0, that's our R. That 3K, when we set a current source to 0, it opens. Now our R is 1.25 K and our C is 8 micro. And now you can simply write the V at infinity plus V of 0 minus V of e to the minus t over RC. And evaluate that at 0.01 seconds. We're going to have to stop. We're way over time. Sorry, but thank you for